Perfect. Listen, thank you for your patience while I got that sorted. Listen, thank you so much for the invitation to be with you today. My name is Alison Keys and I'm a clinical lead speech and language therapist in brain injury services and a dysphagia expert. I'm wearing a slightly different hat at the moment as I'm currently seconded to the Department of Health, looking at workforce education and regulation. But I have a particular area of research focus related to AI and video fluoroscopy. I don't have any disclosures to give other than just some acknowledgements to my colleague Rosalind Rogers in the School of Health Sciences in Ulster University, and also Dr. Orla Duffy and Dr. Claire Rainey from University College Cork, without which their support and expertise, this work just wouldn't have been possible. Just to give you a brief outline of what I'm going to talk about, I'm going to cover what areas of AI swallow phase analysis is currently under development in video fluoroscopy. I'll touch on some of the AI architectures that are being utilised, some of the training and testing methods, and the AI performance of the models. And I'll talk about some of the challenges in terms of AI model development in video fluoroscopy, but we will finish with just what the future opportunities could be. So I was particularly interested in this area and not only wanted to understand and know what AI was being developed for video fluoroscopy, but also for fibre optic endoscopic evaluation of swallowing analysis too. But for the focuses of today, I'm just going to focus on the findings related to video fluoroscopy. And there was a dearth of studies on this topic, and there was only 14 studies that were available to include in the review. As you will be well aware, video fluoroscopies is the most commonly used tool for speech and language therapists to assess swallowing characteristics and kinematics, which helps us plan our intervention and also to mitigate the negative impact of dysphagia. But it happens in less than a second, leaving it really challenging to the human eye. And we know from our studies that the accuracy of that analysis can vary significantly among human subjects. And in this study, there's a range from 45.3% to 71.6% in terms of accuracy. So you can see there is potential in AI to improve our diagnostic accuracy and analysis of the swallow. Radiology is way ahead of the game in this sphere, and there's been substantial advancement of AI tools within your field, and there's deep learning algorithms are showing strong capabilities in medical image analysis, contributing to notable improvements in diagnostic precision, workflow optimization, and overall patient care, as we've just heard from the previous speaker. But AI has the ability to process complex data sets and detect patterns with a level of speed and precision that just as humans we can't. So it does offer us a great opportunity in video fluoroscopy to improve our accuracy, efficiency, and most importantly, the outcomes that we achieve for our patients. Following the advent of deep learning, convolutional neural networks have emerged as a really prominent type of deep neural network, and it's very commonly applied to visual image analysis. And those networks use convolutional layers to automatically extract the relevant features from images, facilitating the classification tasks. And they typically consist of multiple layers that process visual or video data, along with fully connected layers that generate the final output. And it obviously operates within a supervised learning framework where the model is trained on labeled data sets with each input correlating with a corresponding target output. And what's starting to emerge now are three-dimensional CNNs, and they're the ones that are really of interest to me because they're utilised to capture the temporal features of videos as they are capable of processing the sequencing of the video frames and images. And you can see here, ImageNet obviously kicked it all off, followed by AlexNet, and there's a full range now available, and you'll see as we go through just some of the other ones that are being developed. As I started on this journey, I realized very quickly when I was looking at the studies that I needed to understand what AI performance metrics were being utilized so that I could really critically appraise the AI models in the studies that I was using. And you'll hear as I share some of the studies that I found just some of these metrics referred to. So the first one is the performance accuracy, and that is really a primary tool when evaluating the classification tasks. And accuracy presents the ratio of correct predictions to the total number of predictions made by the model, with a higher accuracy generally reflecting improved model performance. So you can arrive at an F1 score that provides a single performance metric by calculating the harmonic mean of both precision and recall. And then we've got mean average precision, which is determined individually by each class, and it's obtained by averaging the values across all classes. Then we've got the DICE similarity index, and it's widely adopted for measuring and evaluating the performance of image segmentation algorithms. It measures the overlap between the predicted segmentation and the ground truth at a pixel level, with a DSI score of 1 indicating a perfect match. And then finally, we've got the Jacquard index, commonly referred to as the Jacquard similarity coefficient or intersection over union, and it's a popular metric for assessing an image segmentation's model performance. It quantifies the similarity between the two sets, and this is typically the predicted segmentation from the AI model, and again the ground truth segmentation, whether it's manual or expertly annotated. And again, a score of 1 indicates a perfect overlap. So what did I find, and which areas of swallow phase focus our AI models being developed for? This slide just gives you a summary of what I found, but there's AI under development for aspiration penetration detection in video fluoroscopy, bolus segmentation, cervical vertebrae detection, hyoid bone tracking, pharyngeal phase detection, and again, of most interest to me, the more recent studies are looking at temporal analysis of the swallow. So just to touch on some of the studies then, looking at aspiration penetration detection, obviously aspiration is a life-threatening complication for dysphagic patients, so the detection of it is really critical to the diagnosis of the swallowing dysfunction. In this study by Lee et al., they proposed a model that consisted of 2 stages. So you'll see here that they developed a model to identify a dynamic region of interest determination, and then as well an airway invasion detection. And this is really interesting because since the head and neck move every time a patient swallows during video fluoroscopy, that's why it's so necessary to create that region of interest that adaptively will move in accordance with the patient's movement. So to that end, this model looked at a cervical spine column showing large and structurally prominent features within each image, and used it as a reference point to define that region of interest. And to locate the cervical spinal column of each video file, a UNet architecture was utilised. And again, it's a really popular and widely used architecture used for segmentation of medical images, and many of the studies utilise that architecture for that purpose. It was also used in this case because it can be successfully trained on a small amount of data. And you'll see as I go through, that's one of the biggest stumbling blocks for AI development in this particular field is the very small data sets that are available. So the second part of the architecture that was developed was for airway invasion detection, and a CNN based on an exception model was used for that, which had data was processed through 3 flows, and it was to deal with the small data sets. It was pre-trained on ImageNet and then fine-tuned through transfer learning. Transfer learning allows the model to learn from a larger data set first and then adapt it to specific swallowing tasks. Interestingly, and the reason that I've mentioned this study in particular, that out of the 4 studies developed for aspiration penetration detection, this model achieved the highest performance score with an overall accuracy of 97.2%. In another study looking at aspiration penetration detection, they had 3 convolutional neural networks, so they had a simple layer CNN, a multiple layer CNN, and a modified LeNet. And that study tested the model on the largest data set out of all the studies that I looked at, with 3,735 image frames looked at. The performance results of the CNNs were compared in terms of areas under curve, and interestingly, the area under curve of 0.974 was obtained for the simple layer, and for the simple layer CNN and the modified LeNet. That was a bit of an unexpected finding, that scored higher than the multiple layer, because you would expect that a multiple layer CNN should have outperformed the other 2 due to the increase in the learning capacity. But increasing the depth of the CNN is known to result in overfitting of the training data, and therefore it can really reduce the generalization of performance. So that overfitting effect may explain the lower performance of the multiple layer CNN in this case when compared to the other 2. In a most recent study, again, that looked at aspiration penetration detection, the authors utilise video action recognition networks to detect aspiration penetration during the swallow, and it incorporated both spatial and temporal information in its model. And you can see here the process used for training that deep learning model using the videos. So there was the training of the 2 stream 3D networks initiated by annotating the region of interest, which after sorting the annotated images according to the time sequence, they were utilised for the deep learning training. Again, a small data set was used in this study. The performance of this model, however, was compared with other up-to-date image models such as ResNet 101, Swin Transformer, EfficientNet B2, and HRNet W32, and it achieved an F1 score of 0.9470, outperforming all those other models that was measured against. Another study looked at cervical vertebrae detection, and the main architecture was ResNet blocks followed by 2 convolutional layers to localize and measure the vertebral bodies. It did yield a high accuracy rate, with the mean distance between the predicted points and annotations being 4.2 and 5.54 pixels respectively. Moving on then from to hyoid bone displacement, and there was a number of studies that looked at this. The most recent study by Lee et al. In 2024 adopted an HRNet to detect the anterior and posterior of the hyoid bone to detect its location and rotation. The anterior and inferior corners of the C2 and C4 4 vertebrae were simultaneously detected to automatically really establish a new coordinate system, if you like. And again, they did that to account for the postural changes that occur in videofluoroscopy. And again, is one of the main challenges that we see in studies that are being developed for video or AI being developed for videofluoroscopy. It achieved an average landmark location error of 2.38 pixels and then an average angle prediction error of 0.065 radians. So again, reasonably promising results. Again, another study looked at hyoid bone tracking. This was interesting because it utilised a cascaded pyramid network to regress the coordinates of the anatomic landmarks, including both the hyoid bone and the vertebrae together, and it was fully automatic, tracking them simultaneously, and can be used to estimate the hyoid bone trajectory and several physical qualities, including the velocity and displacement. And it's that kinematic analysis that for us as clinicians, in terms of analysing that swallow, is so critical to our analysis. This study was also interesting because it was one of the few models that assessed the accuracy of the model using a data set which included various disease etiologies such as stroke, traumatic brain injury, Parkinson's disease, and head and neck cancer. So it very much reflected our real clinical world. And you can see here how the model was trained using a data set of 365 videos from 189 patients. And the results showed high detection rates for the hyoid bone and showed excellent inter-rater reliability for hyoid bone detection, good to excellent inter-rater reliability for calculating the maximal displacement and the average velocity of the hyoid bone. So again, using features like this with AI could simplify our analysis as clinicians, reducing the processing time and really could support clinical decision making. This is another study that again looked at hyoid bone tracking that used a BIFPN UNet network. It showed improved performance when compared with other previous models, achieving an area under curve of 0.998. Another area, and the two final areas that I'm going to talk about, is bolus segmentation. And again, it's very difficult and challenging for an AI model to accurately segment a bolus region in a video image because the images are so translucent, they've low contrast and unclear region boundaries, and they lack colour information. So what these authors did was they utilised a UNet architecture and looked at it against healthy swallow patient and dysphagic patients, and then investigated whether the model could automatically visualize aspiration and penetration findings as well. This study used the smallest data set of only 12 patients. The performance of the model was greater than 0.9, and it did find that aspiration and residual contrast in the piriform sinus were all visualized. In order to overcome the challenges of the image quality that I've just referred to in videofluoroscopy, this most recent study really proposed a very novel AI architecture called PECINet, and that combines two techniques. There's a pre-processing ensemble network and then a cascade inference network. And the pen enhances the sharpness and contrast of the video images by combining multiple pre-processing algorithms in a learnable way. And then the CIN reduces the ambiguity in bolus segmentation by using contrast context from other regions through cascaded inference. So it prevents the undesirable effects from the unreliable segmentic regions by referring to the context in a really asymmetric way. And again, it exhibited higher performance for bolus segmentation than 4 other baseline models that it was compared against. And finally, then, again, the area that really excites me as a clinician, much more recent studies in videofluoroscopy are exploring that temporal analysis of the swallow, extracting information on the timing of the pharyngeal stage of the swallow and the related movements, such as measurement of pharyngeal transit, swallow initiation, upper esophageal sphincter opening and closing, and laryngeal vestibule closure. And again, in this model, the average accuracy of the proposed ResNet 3 was 0.0901, and it again achieved the best results, outperforming VVG and 13D models. And then finally, this was another study, and again, a study that provides good learning for the future. This was a 2024 study by Bashaheen et al. It again employed a UNet architecture, but what it did is it broke down all the temporal events required for swallowing. So it identified the bolus when it was first seen in the oral cavity, the posterior bolus movement, the bolus passing through the mandible, the hyoid burst, bolus tail passing the mandible, the bolus head and the upper esophageal sphincter, and then the bolus tail and the upper esophageal sphincter. And interestingly and disappointingly, it performed the most poorly out of all the studies that I retrieved to look at this area, achieving only a DICE coefficient score of 0.67. Usefully, the authors did carry out additional analysis to characterise the variability of the images and their performance, and really they concluded that the bolus in the oral cavity consistently degraded performance due to misclassification of teeth and unimportant residue. And again, this study really does illustrate the challenges and complexity of trying to develop an AI model for videofluoroscopy, and the challenge does lie in the data set. So, yeah, the challenges for AI model development in videofluoroscopy, it's the scarcity of the data available to train the algorithm and the model. There's a lack of external validation using video data from other institutions. We've talked a lot about today the impact of postural movement on the image quality and the impact that that has on performance and model development. And then you've got discrepancy in image quality due to the varying equipment across clinics and institutions that are used. Added to that, differing videofluoroscopy protocols, including bolus viscosity and diet, and even indeed the level of contrast used. None of the studies that I looked at published the code that they used to develop the model. And really, if that was shared in future studies, it would really allow replicability of the studies with much larger data sets, and again to contribute to clinician trust in those future AI models. As I've already alluded to, AI models for use in temporal swallow analysis show great promise for us as clinicians to support our clinical decision making. Also, that inclusion of patient disease etiologies within the training and data test sets would be really vital. And if that was done, potentially that could be mapped. There could be mapping of extracted clinical features to those individual disease etiologies, which again can facilitate our clinical decision making and prognostication. As you'll have seen, the reporting metrics were vast and different across all of the studies. And again, if we were able to establish standardized reporting metrics and methodologies, that would facilitate much easier comparison and critique across models and training approaches that are being utilized. So thank you very much for your time and attention. There's a reading list there that I can share with Jordan afterwards if the topic is of interest to anybody. But thank you very much for listening.
Thank you so much. I hope you heard the round of applause from our in-person contingent here in Birmingham, Alabama. So Really, really fantastic topic. I was so excited that you came to share this topic with us. We've never covered this before. This is a historically underrepresented field of AI and radiology. So we're covering this topic today, and then we have AI and ultrasound later in the week. So really, really getting filling in some gaps that we've had in our curriculum. So thank you so much. And just as a maybe a funny anecdote. Your topic or your presentation had me thinking about, oh, I wonder what one of these programs would be like at our hospital. And I think that we could potentially reproduce one of those famous AI failures that if we trained on our own data, that we have our outpatient facility where we have a much higher proportion of normal studies that come through as outpatient swallows. And then we have a different machine and a different part of the hospital that has a much more positive inpatient involvement. So I could totally see one of our AI applications finding some sort of just saying, oh, this was done as an inpatient. I'm just going to call some aspiration. I'll probably do I think you covered this topic so well and so comprehensively. If there are any questions, please feel free to put them in the Q&A. But the only one that I had at the very end here was that for such a targeted application, so for video fluoroscopy for these swallow exams, how do you think the practices could sell their health system or sell their hospital on investing into this product or into a product like this? Like, how could they say that this is valuable to their practicing patients?
Yeah, well, obviously our healthcare system here is slightly different, but the reason that I'm hooked on it is because I know the huge resource and cost of dysphagia to our healthcare system as as a region and indeed nationally across the UK. So there are studies that show that the cost to our healthcare system is vast if dysphagia is not managed effectively or optimized, through admissions to hospital, through aspiration pneumonia, or the need for pegs because the swallow hasn't been rehabilitated properly. So it's obviously slightly different, obviously, where you are, Jordan, where everything, is privatized and it's billed and so on. But it does affect a huge number of people that only goes up as our patients and our population increases. So for me, that's why this topic should matter, and that's why we need much more research in this area. And also the other reason I'm really keen for it to see it developed is to increase the access here. It's completely inequitable for patients to access that gold standard diagnostic tool in swallowing. And again, I feel AI could be really utilized to improve that equity of access, particularly in rural communities and people that are not in near large teaching hospitals or clinics and so on. So I think that for me, that's how we could sell the interest and get industry involved in looking at it alongside us.
Oh, I think that makes a lot of sense, and I think that would be similar ultimate goal, but different perspectives. Certainly, in a different healthcare environment. That we're very lucky in this very large, well-resourced health center that we have. We do all these exams in coordination with speech therapy. We review the images in the room, look at them separately on our workstations. And so we have a lot of support and very high quality, in my humble opinion, interpretations of these studies.
Yeah.
But yeah, I mean, you get out into the community, maybe you have people who are less expert in the procedure, they don't have the same level of support. And maybe they just don't even report some of the things that are really critical for management, like having something like this increase standardization and increase quality across the board. I think is really valuable. But thank you so much. This has been a tremendous topic. So we will reconvene tomorrow. Oh, I'm sorry. We have one more question for our in-person audience.
I was just wondering if she's aware of any studies that are targeting the pediatric population, and if specifically if there was somehow AI could reduce the dosage that we use on our pediatric swallow studies.
Oh, that's a great question. I'm not sure if you were able to hear that question, but we had.
Yeah.
Oh, yes. So the question was regarding.
Yeah,
Okay, very good. That's all right.
Yeah, so the question was regarding, if I've heard it right, is am I aware of any studies in pediatric videofluoroscopy with AI models? And the simple answer is no. I have to say, when I used a very systematic method to retrieve the papers, and I have to say, when I put in all the search terms, the number of times that it came back as 0000 was shocking and disappointing. So there's none in there's certainly now I'm trying to think, when I retrieved that data would have been, say, last May, springtime, and at that time certainly I didn't find any pediatric studies then in relation to AI. But absolutely, it's a really valid point, because in terms of being able to reduce that radiation exposure during the procedure for peds.
Opportunity for future scholarship, it sounds like.
There we go.
All right. Well, thank you so much. I see that it's already gotten dark in Belfast, so I hope that you have a good rest of the evening and a good dinner. And thank you so much for joining us.
No, thank you so much for the invitation. Really appreciate it.
Thank you.
We will reconvene tomorrow. I hope everyone has a good rest of the day.